Welcome to the Explainer. So, have you ever actually wanted to look, completely under the hood of a massive AI, like taking its engine apart piece by piece just to see exactly how the gears turn? Well, today, we are embarking on a really fascinating journey right into the core of an artificial intelligence. We're going to explore developer Jeffrey Redd's open-source mini transformer repository. And listen, this isn't just abstract theory. This is a hands-on blueprint for building a GPT-style causal transformer entirely from scratch. If you've ever wondered how large language models actually process and generate text at a fundamental level, you are absolutely in the right place.
Okay, let's just dive right in. Here's our game plan for today. We'll start inside the mini transformer, fix word order, enforce some no-peeking rules with causal masks, optimize with stacking and weight tying, cover training and generation, and finally, look at how this acts as a stepping stone to GPT-2.
Just to give you a little bit of context here, this mini transformer repository is actually the crucial third step in a much larger 7-part mini LLM series. Step 1 tackled your basic word vectors, and Step 2 introduced a really simple multi-head self-attention block. But now, here in Step 3, things get incredibly exciting. We are taking those foundational pieces and assembling them into a true, functioning language model that can actually generate sequences. We're not going to get bogged down in the old steps, but it's really helpful to know exactly where we are on this big roadmap toward building a full mini-chat application.
All right, let's kick things off with Section 1. Inside the mini transformer, we are going from basic attention to a true language model. We are officially stepping up from those simple, isolated self-attention blocks to a full-blown causal decoder. This is literally the leap from a model that just looks at words to a model that can actually write them. I mean, just look at the sheer scale of the upgrades we're making here. In the old setup, we had this basic single block using a simple ReLU activation, and it totally lacked the structure for actual sequence generation. But look at the mini transformer. We're stacking 2 blocks for much deeper understanding. We are swapping to GELU activations, which, by the way, is exactly what modern large language models use today. We're also bringing in special tokens, beginning of sequence, end of sequence, and pad. Think of these like essential traffic lights, telling our AI exactly when to start thinking and when a thought is entirely finished. It's a massive leap forward. Moving right along to Section 2, fixing word order and giving the AI a sense of sequence. Now, before this shiny new architecture can truly understand language, we've got a really fundamental problem to solve. Because as it stands, basic self-attention has absolutely no concept of sequence or time. Let me just ask you this directly. How does the AI know the difference between the phrase, "cats like I" and "I like cats"? To a basic self-attention mechanism, these two sentences look completely identical. It just sees a big bag of words and treats every position equally. If we actually want our AI to generate coherent sentences, it desperately needs to understand that the order of words changes the meaning entirely.
So the crucial point is how we inject that sense of time. And the answer? Positional encoding. Before our words even enter that first transformer block, we take their embeddings, which, remember, represent their underlying meaning, and we mathematically add a unique, fixed, sinusoidal vector to them. Think of it like stamping a completely unique mathematical barcode onto every single position in the sentence. And because these are fixed mathematical waves, not learned parameters, they beautifully generalize to sequence lengths the model hasn't even seen during its training. Suddenly, boom, the AI knows exactly where every single word sits in the lineup.
Which brings us to Section 3, no peeking, causal masks. We are forcing the model to predict the future. If we're training our AI to predict the next word in a sequence, we have to lay down some strict ground rules. Specifically, we have to restrict what the model is allowed to see during its training phase. Let's break down how we enforce this conceptually. We use what's called an upper triangular Boolean mask. Imagine a giant grid comparing every word in a sentence to every other word. This mask literally drops a mathematical wall right over the future words. If the model is currently analyzing the word at position I, this mask strictly prevents it from attending to or peeking at position I+1, I+2, and so on. It physically blocks the AI from cheating. It is forced to guess the next word relying solely on the context of the words that came before it. And honestly, as the author's documentation perfectly summarizes it, this is what makes the model a language model. Relying exclusively on past context to predict the future is the absolute defining trait of text generation. It mimics exactly how the model has to operate in the real world later on, where the future words simply haven't been written yet. All right, Section 4, stacking and weight tying. It's time to refine and optimize this network.
Now that the foundational rules of time and causality are securely in place, we can focus on refining our network, making it not just functional but way smarter and way more efficient. First up, stacking. Instead of passing our data through just one transformer block, we run it through two in sequence. Layer 2 takes Layer 1's output directly as its input. This compounding power is just incredible. It allows the later layers to build upon the really complex representations and relationships established by the earlier ones. In fact, if you check out the visualizations from this repository, you can visibly see how Layer 2 brilliantly refines the raw attention patterns that Layer 1 initially found.
And this brings us to a really elegant trick in modern AI design: weight tying. At the very end of our model, we need an output projection to map the AI's internal mathematical thoughts back into our human vocabulary of words. But instead of creating a massive new set of parameters for this, we simply share, or tie, the weights with the input embedding matrix we used way back at the beginning. This clever little trick drastically reduces the overall size of the model, saving us a ton of valuable memory. Plus, it stabilizes the training by forcing the model to learn a highly consistent representation between the input space and the output space. It's a standard optimization trick that you're going to find in GPT-2 and almost all modern language models today.
Section 5. Training and Text Generation. Let's actually put this mini transformer to work.
Okay, we've covered a lot of theory and architecture. It's time to shift gears and look at the concrete code and the exact configurations required to actually fire up this engine yourself. If you look at the configuration table here, you're going to see a few critical settings. We have an embedding dimension of 32, which is larger than the previous steps. That's going to give us beautifully clean visualizations of those positional encodings, but pay special attention to the number of heads, which is set to 2. A really strict mathematical rule of this architecture is that your number of attention heads absolutely must divide your embedding dimension perfectly evenly. We also see parameters for learning rate warmup, a crucial 50-step linear ramp up to our peak learning rate. Transformers can be notoriously unstable right at the beginning of training, and this warm-up phase essentially prevents the model from mathematically exploding before it even gets off the ground.
And the coolest part, when you actually hit run on this repository, you don't just get a boring wall of text, you get this amazing suite of visual outputs. The code automatically generates your saved model weights, obviously, but it also creates a stunning heat map PNG of your sinusoidal positional encoding matrix. It generates graphs that track your training loss and perplexity, letting you verify that the model is actually learning something. And my absolute favorite feature, it outputs an animated GIF showing the attention mechanism of a specific head evolving in real time as the training progresses. You can literally sit there and watch the AI's brain wiring itself together.
Once that training is totally complete, the repository opens up an interactive generation prompt, and it gives you some seriously powerful flags to play around with. You can use the greedy flag to force the AI to just always pick the most mathematically probable next word, which gives you very predictable text. Or you can adjust the temperature and the top K flags. These are basically dials for the AI's creativity. They allow it to sample from slightly less probable words, generating much more diverse, natural, and sometimes really surprising text. You have total, complete control over how it behaves during inference.
And finally, Section 6, Stepping Stone to GPT-2, the theory and what comes next.
Listen, it's so important to realize that this mini transformer isn't just a fun little toy. It is a direct foundational bridge to some of the most world-changing AI papers ever published. The repository includes a file called theory.md, and I really highly urge you to go explore it. It gives you this intense conceptual deep dive into the real nuances of the architecture. It explains advanced stuff like why modern models use pre-norm instead of post-norm residual connections. It maps literally every single line of code you just ran directly onto the architecture of OpenAI's legendary GPT-2 model. It completely demystifies the incredibly dense concepts from the famous "attention is all you need" paper, and it turns all that abstract academic math into accessible, runnable Python code.
We've seen exactly how stacking blocks, fixing word order with mathematical barcodes, and enforcing strict causal masks can take a simple attention mechanism and turn it into a powerhouse generation engine. It's just an incredibly elegant system once you break it all down. So I want to leave you with this final thought. Are you ready to download this repository, dive into the code yourself, and literally build the mind of an AI entirely from scratch? The blueprint is right there, waiting for you. Thanks for joining me on this journey under the hood today, and keep exploring.